Okay, welcome back, students. Let's continue on to section 4.8, row space and column space. Okay, let me share my screen. So 4.8 is on row space and column space. Okay. So definition for any A, an element of M by N of R. Okay, so any M by N matrix, A is an element of any M by N matrix. Okay, A is any M by N matrix. Okay, the span of row vectors of A is called the row space of A. And is denoted as row space of A. Okay, this is a subspace of Rn. Okay, likewise, the span of column vectors of A is called the column space of A. Uh, denoted as COL space, col space of A, and is a subspace of Rm. Okay, because there should be M rows and N columns. Okay. Okay, theorem. Okay, let A be an element of M by N of R. So that's our vector space that A is an element of. Okay, we already know that's a vector space. If B is any row echelon form of A, then the row vectors in B containing the leading ones decided that's the word, ones, the leading ones, give a basis for the row space of A. For B, column vectors in B containing the leading ones. Oh, sorry, this should be A. The column vectors of A, I don't know why I wrote B. Okay, the column vectors of A containing the leading, this is wrong too, sorry, my bad. The column vectors of A that correspond to the column vectors in B containing the leading ones give a basis for the column space of A. Okay. Okay, let's do an example. 1. Now let A equal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, then I want to REF this. Okay, reduced, oh, sorry, not reduced. Row echelon form. We just want row echelon form of this matrix. Okay, and so let me plug that into my calculator. Okay, so let's go to matrix, edit. Oops. Edit. I want this to be a 3 by 4. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, second quit. And I want to REF this, not REF, REF. So matrix, math, I'm gonna go arrow up until I hit REF, row echelon form, that's letter A. Okay, and then I would need to call up my matrix, matrix A. Okay. Okay, and I'm gonna get some decimals there, so I want to change that to a fraction, so I can go math to fraction, and so it gives me that nice matrix there. Okay, so let's go back and look at our matrix, our resulting matrix. It was 1, 10 ninths, 11 ninths, and 12 ninths, which is 4/3. Okay, so 9 ninths, 10 ninths, 11 ninths, 12 ninths. Okay, 0, 1, 2, 3, and then 0, 0, 0. Okay, row of 0. So this is linearly dependent. So we get that row of zeros. The determinant would be, well, it's not, we wouldn't have a determinant here, but it is linearly dependent. So because of the row of zeros. Okay, so what is the row space? Okay, row space of A. So the row space of A, okay, is the span of row vectors of A. Okay. Okay, so if we row echelon this, the row vectors in B containing the leading ones give a basis. Okay, so that's the basis. We don't want that. We just want to know what does this, what's the span? What's the span? Well, I can just write the original row vectors as the span for any A, Mn. The span of row vectors of A is called the row space of A and is denoted as row space of A. Okay. So, yeah, so we just use the original matrix to get the row space. So the row space, okay, of A are just the rows, the original rows, written as vectors. So this is the span, okay, the span of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that's the row space. Okay, what will be the column space of A? The column space are just the column vectors. Okay, so it's the span of 1, 5, 9. Now we're doing columns. Okay, and then 2, 6, 10. And then we have 3, 7, 11. And then we have 4, 8, 12. Okay, so that's the row space and the column space. Now let's find the basis for the row space. Okay, what would be a basis? Well, because when we RREF it, we only get two unique rows, okay, that have leading ones. Okay, then I could get all three of these. I could create all three of these rows, okay, from any two. So that just tells me that my third row could be a linear combination of the other two. Okay, and so that's kind of interesting. Okay, so we only need two row vectors to form a basis for the row space. Okay, we only need, because there's only two linearly independent vectors here. Okay, the third one is a combination of the other two. Okay, okay, so the basis, or a basis, I should say, a basis of row space A is equal to, okay, these row vectors. Okay, so 1, 10 ninths, 11 ninths, and 4 thirds, and then 0, okay, 1, whoops, 0, 1, 2, 3, okay, and that's in R4. Okay, So the dimension of the basis, okay, it's in R4. Okay, because there's four unique entries there for each of those vectors. Okay, so now what about a basis for the row space? I mean, basis for the column space. A basis of the column space of A. Well, that tells us to look at the leading ones, but now that's going to point me back to my original vector, my original matrix. Okay, my original column. Okay, column vectors. So if I have leading ones here for the row space, I use the row echelon form for the rows, but for the column space, I actually use the original. But I only choose the columns that have leading ones. Okay, and so this is going to be 1, 5, 9, and 2, 6, 10. Okay, those are the only linearly independent vectors in that matrix. Okay, and so that is in R3. Okay, so the column space is in R3, but the row space, the basis of the column row space is in R4. The basis of the column space is in R3. Okay. Okay. What about the dimensions? The dimensions of the basis of the row space of A. Okay, so the dimensions of the basis of the row space of A, well, again, that's how many rows I have that don't have any zeros. Okay, they're not full zeros, and that's 2. Okay, so that's 2, or in this case, 2 vectors. Okay, and then what about the dimensions of the column space, or the basis, sorry, I should say, the basis of the column space of A? That's also 2 vectors. Okay, and it's based on the leading ones. If I only have 2 leading ones, then the basis of the row space is going to have 2 vectors, and the basis of the column space is going to have 2 vectors. Okay, so these are always equal to each other. Okay, so, always equal. Since they're based they are based on the number of leading ones in B. Okay, matrix B there. Okay, let's look at number 2. Okay, determine a basis for the subspace spanned by the given vectors by using row space first and then column space. So using the row space first and then the column space. Okay. Okay, so we're gonna say that S, okay, the subspace spanned by these vectors. So the spanning set is 1, 2, 3, 4, 5, 6, and 7, 8, 9. Okay. For the row space, the vectors are rows. Okay, for row space, the vectors are rows. Okay, so A would be equal to 1, 2, 3, 5, 6, 7, 8, 9. Okay, and when we REF that, we would end up with 1, 8 sevenths, 9 sevenths, 0, 1, 2, and then 0, 0, 0. Okay, so a basis for the row space of A. Okay, so it says determine basis for the subspace spanned by the given vectors using the row space first and then the column space. Okay, basis for the row space A is equal to the rows that contain the leading zeros. So this is going to be, oops, 1, 8 sevenths, 9 sevenths. Okay, and then 0, 1, 2. Okay, in R3. Okay, now to find the basis, a basis using these vectors that they give me. See, they gave me vectors originally, not a matrix. If they give you a matrix, then you have to use the matrix. Okay, but if they give you vectors and you want to, okay, use these vectors as columns, okay, to find a column space, the basis for the column space, then we have to choose the vectors to become column vectors, okay? So we're going to create a different matrix here based on the fact that we're designating these vectors in S 1, 2, 3, 4, 5, 6, 7, 8, 9 now as column vectors. Okay. And so I know it's a little confusing because when we did it before, we used one matrix to give me both my row space and my column space. But now we're just using a set of vectors that span, okay, we want to determine a basis for the subspace spanned by these given vectors. And so we're going to create one that is a column space based on these vectors that are now columns. Column vectors 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And then when I REF that, I actually end up with 1, 2, 3, 0, 1, 2, 0, 0, 0. Okay. So what is my column space? Or what's my basis, I should say. My basis for the column space of C that I've now created out of these vectors. These vectors, the first time we were talking about rows, so we let the vectors be rows and create a matrix out of that. The second one we're talking about columns, so we're going to create a matrix out of the columns, let the vectors be columns. But so the basis for the column space of C, okay, well, it's gonna correspond to my leading ones, but it goes back to the original matrix C that I created. So the base of the column space of C is equal to 1, 2, 3. Okay, and 4, 5, 6. Okay, in R3, because they each have 3 components. Okay. Okay, so let's do one again where they don't give us the vectors. They actually give us a matrix. Let's do one last one here. Okay, number 3. Determine a basis for the row space of A and a basis for the column space of A. Okay, and so what is matrix A? Well, matrix A happens to be a 4 by 5 matrix, so it's a big matrix. 1, 2, -1, 2, -1, 2, 4, -2, -3, -1, 5, 10, -5, -3, -1, -3, -6, 3, 2, and 1. Okay, now since we're locked into the matrix, okay, again, they don't give us the vectors, and we don't get to choose the orientation of the vectors because we already have the matrix locked in. Then I'm gonna REF this. Okay, and again, I'll go to my calculator to help me out. So the matrix, I want to edit this. This is now going to become a 4 by 5. Okay, and that's going to be 1, 2, -1, 2, -1, 2, 4, -2, -3, -1, 5, 10, -5, -3, -1, -3, -6, 3, 2, 1. Okay, second quit out of that. And I'm going to REFA. So I'm just going to grab it from up here. REFA, boom. And then I'm going to make that a fractions, so it's a little more concise. So math, enter, enter, and we get that one. 1, 2, -1. So there's only 2. There's only 3 rows with ones. Okay, I mean 3 columns with ones, 3 rows with ones, and 3 columns with ones. Okay, I only have 3 leading ones. Okay, so 1, 2, -1, -3/5, 1, -1/5, and then 1 and -4, 4/13, and then a 1. Okay, so let's write that down. So this is going to become 1, 2, -1, -3/5, -1/5, 0, 0, 0, 1, 6/13, 0, 0, 0, 0, 1, and then a row of zeros. Okay, so what's the basis for the row space of A? Okay, that's going to be my rows that just contain ones. So, and each of them are going to have five elements or 5 components. Okay, 1, 2, -1, -3/5, and -1/5. Okay, the next row is 0, 0, 0, 1, and 6/13. And the last row is just all zeros. 1, 0, 0, 0, 0, 1. Okay, and that is my basis. Yeah, that's my basis in R5. Okay, what about my basis from my column space of A? Okay, well, that's gonna, I have this row, and this row. Okay, and that's gonna go point back to the first row, the fourth row, and the fifth, I'm sorry, the first column, the fourth column, and the fifth column. So that's gonna be 1, 2, 5, -3. 2, -3, -3, 2, and -1, -1, -1, 1. Okay, and that's in R4. Okay. Okay, so that's row space, column space, basis for row space, basis for column space. Okay, and I'll see you in the next section.